Today we're taking a look at lab number 7, binary arithmetic. We're going to be using some basic gates, and there is one textbook change. Your textbook uses the 7483. We're going to be using the 74283. So chapter 8 of your textbook talks about binary arithmetic, and we're talking here about binary addition, and they give you some rules for binary addition. In decimal, we do 9 plus 1, and we automatically know that the answer is 10. But notice the answer, if we line the columns up, is 0, and there's a carry bit. So 9 plus 1 equals 1 carried and 0. In binary, the number 1 plus 1 equals 0, and we carry the 1. So this is the carry bit being set. So your textbook gives you a little truth table for the half adder. You notice in your textbook the half adder circuit can be represented by a box, and they just label it as a half adder. Notice there is a sum and a carry out. We're going to be using individual logic gates to build our circuit. Part A of the lab is the half adder, and basically what we're doing is we're adding two 1-bit numbers together. And when you add two 1-bit numbers together, you end up with a sum. So it's the total of the two numbers added together. And because we're using binary, if the sum is greater than 1, we have to go to a carry out bit. So in this particular schematic, we can see that there is actually going to be two outputs. For the lab schematic, part A, the half adder, I've filled in my pin numbers. So on the truth table that I've provided you with, we're going to have two inputs, A plus B. So input for A, input for B, and we want to know what the sum is and whether the carry out bit is on or off. I've wired up my circuit following my schematic. My first switch is A. My second switch is B. The red LED is the sum, and I've used a green LED to represent carry out. In the first case, where I'm inputting 0 plus 0, my output is 0 with no carry. On the second line of my truth table, the input is 0, 1, and my output is 1 with no carry. On the next line of my truth table, A is 1, B is 0, my output is 1, and my carry is 0. In the last line of my truth table, A is 1 and B is 1. My output is 0 and my carry bit is on. 0 plus 0 equals 0. What would the carry out be? There is no carry out, so that would be a 0. 0 plus 1 is 1, still no carry out. 1 plus 0 would be 1, still no carry out. And 1 plus 1 would be 0, and the carry out bit should be set to 1. Once you've wired up your circuit for part A and verified that it is working, demonstrate it to your instructor so that they can initial it to indicate that it is complete. In section 8.3 of your textbook, they talk about binary subtraction, and in figure 8.10 they give you a nice example of using the borrow. And you can see in figure 8.12 they give you the diagram for the half subtractor, and it can also be written as a block symbol, and they just label it HS. It still has two inputs, so two inputs, and two outputs, the difference and the borrow. So part B of the circuit, I have a schematic set up here for a half subtractor, and you'll notice that we've changed the names of the outputs. It's no longer the sum and the carry. It's now called the difference and the borrow. And it's very important to put your pin numbers down. So this is my circuit for part B, the half subtractor. I want you to notice that I put the inverter after my output LEDs. Most of the circuit stays the same. It's just the A input that goes to pin 1 on the 7408 goes to the inverter first and then comes back to the 7408. Now I've wired up my circuit just like my truth table. So the first switch is A, the second switch is B. So you're subtracting B from A. So it's A minus B. And over here on my outputs, my red LED is going to be the difference, and the green LED is going to be the borrow. So this is my 7486, the exclusive OR. This is my 7408, the AND gate. And the output of the AND gate goes to the borrow. For the first condition, where I'm doing 0 minus 0, the output is 0, and there is no borrow. If I do 1 minus 0, the answer is 1 with no borrow. If I do 1 minus 1, the answer is 0 with no borrow. But if I do 0 minus 1, the answer is 1 with the borrow bit set. So, filling in the truth table, 0 minus 0 was 0, and the borrow bit was not set. 1 minus 0 was 1, and the borrow bit was not set. 1 minus 1 was 0, and the borrow bit was not set. 0 minus 1 was 1, and the borrow bit was set. This is identical to the answer given in figure 8-11 for the half subtractor. Once you've wired up the circuit for part B and verified it is working, demonstrate it to your instructor so that they can initial it to indicate that it is complete. Your textbook gives you the block symbol for a full adder. And as you can see, there are 3 inputs, 2 outputs, the sum and the carry out. Figure 8.5 in your textbook shows you how 2 half adders are wired together to create a full adder circuit. A full adder circuit has an A and B input and has a carry in. The carry in would have come from the previous half adder circuit. The full adder circuit was taken from your textbook. It's figure 8.6, where they give you the logic diagram of a full adder. Part C of your lab is the full adder. So in the full adder we have our A and B input, but we also have the carry in. So now you can see we've doubled the size of our circuit, we still only have two outputs, the sum and the carry out. It is highly recommended that you fill in the pin numbers, and when you're wiring this circuit, use the highlighter to mark the lines that you've already wired up. The truth table for the full adder has inputs A, B, and the carry in, which would have been from a previous circuit, and the outputs are sum and carry out. So this is my circuit for the full adder. I have here the 7486, the 7408, and from the last circuit we had the 04 inverter. Now I've replaced it with the 7432, the OR gate. My input switches are A, B, and carry in. My outputs are going to be the sum, and I've used the green light for the carry out. You'll notice keeping the wires short helps you to see where all the wires are going, rather than leaving the wires long and it looking like a big bowl of spaghetti. A big bowl of spaghetti is very hard to troubleshoot, so I recommend you keep your lines short like I've done here. So this is the schematic for part C, the full adder. You'll notice that I've put down all the pin numbers, and because this is a fairly confusing circuit when you try and wire it up, every time I've wired up a wire, I've highlighted it in yellow. So you notice that C goes to pin 1 of the 86. It also goes to pin 1 of the 08. So once you've wired those two wires up, I would go over it with a highlighter. So you can get fairly confused trying to wire this circuit up if you don't have some way to account for each wire that you've put in, and going over it with a highlighter helps me. So right now I have 0 plus 0 with a 0 carry in. So if I have 1 plus 0, the sum light comes on. If I have 0 plus 1, the sum light comes on. If I have 1 plus 1, the sum is 0 and the carry is on. If I start with the carry in at 1, you can see my sum is already 1. If I make A 1, you can see that A being 1 plus 0 plus the carry in bit gives you a sum of 0 and a carry of 1. And if I have 0 plus 1 with the carry in, I have a sum of 0 and a carry of 1. If I have 1 plus 1 with the carry in, the sum is 1 and the carry out is 1. So back on my truth table, 0 plus 0 gave us a sum of 0 and a carry of 0. When I have 0 plus 1, the sum is 1 and the carry is 0. When I have 1 plus 0, the sum is 1, the carry is 0. When I have 1 plus 1, the sum is 0 and the carry bit is set. Then when I have a carry in, 0 plus 0 plus the carry in bit gives me a sum of 1 and the carry out is 0. 0 plus 1 with the carry in bit set gives me 0 sum and 1 on the carry out. 1 plus 0 with the carry in bit set gives me 0 with a carry out bit set. And when I have A is 1, B is 1, With the carry in bit set, the sum will be 1 and the carry out bit will be set. The truth table for the full adder is figure 8.5 in your textbook. Once you've wired up your circuit for part C and verified that it is working, demonstrate it to your instructor so that they can initial it to indicate that it is complete. Chapter 8.4 in your textbook gives you the information you need to know about parallel adders. Figure 8.19 in your textbook shows you a 4-bit parallel adder using 4 full adders. Figure 8.21 in your textbook talks about the 4-bit parallel adder. One of the books on my bookshelves is the TTL Data Book, Volume 2. When I was a student, data sheets used to be published in books. So this is the data sheet for the SN, and you can see it's the SN 5483 as well as the SN 7483, 74LS 83, the 4-bit binary full adders with a fast carry. You can see the pinouts for this particular IC, and you'll notice that power came in on pin 5 and ground was on pin 12. The 74LS283 are recommended for new designs as they feature supply voltage and ground on corner pins to simplify board layout. So the 74LS283 is the 4-bit binary full adder with fast carry, and you can see that they've changed VCC to pin 16 and pin 8 to ground. Also in these books, they always used to give you a logic diagram. So this was the logic diagram for the 283, and you can see these are the inputs and these are the sum outputs, and right at the top here we have the C4 carry out. So over time they discontinued making the 7483, and it was totally replaced by the 74283. So that's why we're using the 74283 in our lab instead of the 7483. So this is the lab schematic for part D using full adders. This is the 4-bit parallel adder, and it's all on one IC. I just want you to notice here that C0, that's your carry in. That would be a carry in from a previous IC. Our carry in is going to go to ground because we want to input a logic 0. So a lot of times students will wire up pin 8 for the ground, and they'll ask, why do you have a second ground in there? It's not a second ground, it's a logic input to the carry in. So C4 is your carry out bit, and that's going to go to a green LED. Your sum 1 comes over here to the first LED, and your sum 4 comes over here to the LED beside the carry out bit. You'll notice I've drawn the switch as a dip switch package, and I did this because I want you to notice that we're going to have two inputs, an A input and a B input, made up of 4 bits each. So these are 2 hex numbers that we're going to add together. B1 is your last switch. A1 is your 4th switch. So I'll point that out to you in my circuit. On the truth table, I have input A and input B, and I've given you hex numbers. So you need to know that the number 4 in 4-bit binary is 0, 1, 0, 0. And the number 3 is, the number 3 in 4-bit binary is 0, 0, 1, 1. We want the answer in hex, but we're going to get our output in bits. So this is sum 1, sum 2, sum 3, sum 4, and this is the C4 or carry out bit. So this is my circuit for the 4-bit parallel adder, and this LED at the end here is going to be the ones, or sum 1, sum 2, sum 3, sum 4, and the carry out bit. The input switches, because I'm using 8 switches, I need 8 grounds, 1 ground for each switch. I need the ground wire for the IC, and this is pin 7. That's the C0 line, or the carry in line. And we said that was going to be logic 0. So that's the second ground. The second ground is actually a logic input. Now on our schematic we saw that pin 6, so 1, 2, 3, 4, 5, 6, which is this yellow wire here, went to B1. So this yellow wire goes to B1. So this is B1, B2, B3, B4, followed by A1, A2, A3, and A4. To test the circuit out, I can put a logic 1 on B, and you can see that the first LED is on. If I put a logic 1 on A1, 1 plus 1 should equal 2. So in the example that I've given you on the truth table, A has to be 4. So 4 is 0, 1, 0, 0. And B is 3. 3 is 0, 0, 1, 1. And the answer is 0, 1, 1, 1, which is equal to 7. So on the next line we want 5 plus 5. So 5 is 0, 1, 0, 1. And 5 on B is 0, 1, 0, 1. The output, we can see the carry bit is not set, and we have a 1, 0, 1, 0. 1, 0, 1, 0 is A. So on our truth table, the first LED was off, the second LED was on, the third LED was off, and the fourth LED was on, and our carry bit was 0, or off. So 1, 0, 1, 0 happens to be A. For the hex output, the answer is A. 5 plus 5 is equal to 10. 10 in hex is A. If you're having trouble remembering what those hex numbers are, you might want to write them down on the side of your page, starting with 0001 is 1, 0010 is 2, all the way down to 1111 is F. Once you've wired up your circuit for Part D and verified that it is working, demonstrate it to your instructor so that they can initial it to indicate that it is complete. On the last page of the lab, we have 8 questions for you to answer and hand in. If you are looking for answers, open your textbook. Page 1 of the lab shows some hints. And in this case, we're looking at Solve Problems, section 8.1 to 40, 59 to 66, and 83.